Okay, so the first presentation is given by Xianglin. So this is the NIPS 20 papers. It's about the model explanations and test debuggings. Yeah, please go on.
Yeah, so the paper I'm going to present today is called Debugging Test for Model Explanation, and it is recently just been published in NIPS 2020. NIPS 2020. Yeah, so the first author is called Julius, and he's a PhD at MIT. But I find it interesting because the rest of the authors are not from a computer science background. They are more from a
Psychology.
psychological
Mm.
research area. So I assume all the experiments are done by the first author. So the background part, I need to first clarify some terminology. So when I mean model debugging, it means to diagnosing and fixing model errors. And in this paper, we said model explanation or feature attribution method. They are just artifacts derived from a trained model with primary goal of providing insights to an end user. I will give more examples about explanations later. And nowadays more research began to use explanations for model debugging. But here comes a question. Few research has answered the question, which explanation methods are the most effective for which classes of model bugs? So this question is the problem that this paper tries to address. In order to answer this question, first, we need to answer how to define model bugs. What classes of model bugs are there? So their first contribution is to do bug categorization, and the second question is what options do we have? What do we have? What kind of explanation method do we have? So the second contribution is to do a empirical assessment of not all, but I would say a lot of existing state-of-the-art explanation methods. And the third question is how to define effectiveness of those model explanation methods. Because when you think about it, it's very hard to write a program to automatically calculate a score for effectiveness. So in order to solve this problem, they do a human study to assess the reliability of models using those attribution methods.
Mm. Yeah, so these questions are all very important and supposed to be very helpful for our own research. Yeah, good selection.
Yeah. So the first part is bug characterization. First, if you look at training the neural network as a optimization problem, you will first have your training data, some samples along with its labels, and then you will have your model here represented as parameters data. And finally, you would use you will use the data you learn from the training data set to predict the labels for some testing data set. So what they do is they characterize the bugs into three classes, including training data contamination, model contamination, and test time contamination. And for each classes, they split it into two subclasses. In terms of training data contamination, they have two subclasses called labeling errors and superior correlation. So labeling errors just means you have some mislabeled data in your training data set. So that might cause some problem when you train the neural network. And the second one is called superior correlation or wrong correlation. That means, for example, if you have a class of plane, but all the images for class plane are have a background of blue sky. So basically, all planes are set in a blue sky. So that means the model might learn that relation. And in the test time, if you are given a picture only contains blue sky, that model might still characterize that picture as plane. So that means spurious correlation. And for the model contamination, that means reinitialized weights or unintentionally frozen layers. So they think if you have some bugs in your code and you might unintentionally reinitialize weights or unintentionally frozen layers, but you don't know if it happens. And for the test time contamination, there are two subclasses. One is called out of distribution data. That means, for example, if you train a model to classify digits, means data set. However, in the test time, you give it a image from CIFAR 10, then the image from CIFAR 10 is called out of distribution data. And the last one is called mismatch in pre-processing. And that means the testing data do not have the same pre-processing process with the training data set. So suppose when you are train a data set, you would calculate the mean and standard deviation. And that's supposed to be the same in your testing data. But if you use a different mean and standard deviation, that would cause the mismatch in pre-processing. So the 6 classes of bugs are discussed. But
so it's very good practice that we define our problem scope here. But here the model contaminations.
yeah, it's weird. Right.
Yeah, so how could be there's any intended layers or you mean the reinitialized weight in the programs accidentally reinitialize the weights.
Yeah.
So that's more like the traditional bug, right? So that's more like a traditional bug. So in terms of the when of course the deep learning program is still a kind of program, but it will be very different. So the model bug usually infers this more. I think here. So I just say my opinion may not be
I
correct.
know.
So first the blue one, the training data. So the labeling errors and the spurious correlations, and the out of distribution data were supposed to be more model relevant, while
More irrelevant.
more relevant to the bug, the model bug or the deep learning model bug in my mind. And as for the reinitializing weights and unintentional frozen data and mismatching pre-processing, it's more relevant to the traditional bug. For example, when I'm writing code, I miswritten some code, so I miswritten some code so that the true condition becomes false. So I accidentally reinitialized the weights and frozen the layers, and I forgot to process some test data, and that is all the engineering bug or traditional bug. So I just wanted to. Okay, please go on.
But they didn't address those problems in this paper.
So okay, so they are just showing an empirical study, or anyway, they're psychologists.
I think they don't have any proofs. All they did is a lot of empirical assessment and see which explanation can find those bugs.
Yeah, especially for our case, I'm not sure whether we need to conduct a human study too. Not sure. So in that case, suppose we have visualization technique. If possible, I think the user study or human studies might be helpful. to improve the convince. But anyway,
Mm-hmm.
the human study involved a lot of effort. We need anyway, we talk about it in individual meetings here. So please go on.
Yeah, and even though I talk about 6 kind of bugs here, but actually later in their assessment, they only focus on 4, the spurious correlation and labeling errors, reinitialized weights, and out of distribution error.
Okay.
And then the next part is to briefly explain the model explanations. So what model explanation means is that they kind of provide a relevance score for the dimensions of input towards a model's output. So how to interpret that means if you have a feature attribution method or explanations, you are given an original image and its prediction, and then the attribution method would output one feature map that has the same shape with the original image. But in the feature attribution map, each pixels represent how important is it for the original, how important of the original pixel for the given prediction. So yeah, here is the visualization of some attribution maps. Is that clear? But anyway, so every attribution method would output one heat map and showing which part of the original image is most important for the final prediction. But the method they use is different.
So in this paper, they look into how many of them? So it's supposed to be 15.
1, 2, 3, 4, 5, 6, 7, 8, 9.
15 of them. So they're all about attribution, but I didn't see the the integrated gradients here. Is there?
Here. It's
Okay.
in first 1, 2, 3, 4, 5, 6.
Okay.
The 6th one.
Okay, integrated gradients is here. And what's we're supposed to report another paper about attribution methods, right? The
ACE.
ACE, yeah.
Average causal effect.
Yeah.
But they didn't include that in this paper.
Yeah, maybe it's too
Too new.
expensive. Too expensive.
Or too expensive.
Right.
Maybe.
Okay, keep going on.
So briefly introduce those kind of attribution method. So they first categorize all the attribution methods into 3 classes. And the first class is called gradient and its variance. So the first one is just a gradient. And the second one is called smooth grade. So what they did is they add some Gaussian noise to the X and compute the average of gradient. And the third one called S grade square. So it's just the element-wise square of smooth grade. And the fourth one is a variance analog of S grade. Yeah. Actually, I don't know what it means, but it's supposed to be one of the methods. And the fifth one is input grade. So it means you calculate the gradient and times your original input. And the sixth one is the integrate gradient. We've had a presentation about this paper, so if you don't know the details, you can check that presentation. And the seventh one is called expected gradient. So the difference between it and the integrate gradient is that in the integrate gradient, the x bar might be 0 or 1. However, in the expected gradient, they exchange the x bar to the expectation of the whole training data set.
By the way, what is the expectation? How do they define expectation there?
I guess they just summarize, sum the whole training data set and.
Right. So how do we define? So here the baseline is a sample, right? So we only have expectation for the label of a sample, and we have no expectation for the sample itself. So that's what I understand.
I think, for example, if you have 100 training data, then you sum all of them and divide it by 100. That's the expectation, right?
And why? What benefits does this give me?
Huh?
And why is there? I know my question is out of the scope of this paper, but is that possible to see why the average can bring less benefits as a, so more like baseline, right?
Yeah,
So the
they
X
change
bar
the
here,
baseline
the X bar is baseline, and when X bar is 0, that will be understandable. But when X bar is something like an average, I didn't quite get it. And also, if X bar is the zeros, so the results of the gradients can change from dataset to dataset. But
Yeah.
I don't know.
I didn't check that paper, but I think you need to find a baseline that is irrelevant to any other data. So
And also, you can look at the effect. Maybe that was just individual case. I think the effect of integrated gradient seems to be better than, right? It's better than the expected gradient. I'm not sure. What's going on? Yeah,
yeah, I don't know, but
I
that's
encourage.
not the point.
Yeah, I encourage other student who is not familiar with integrated gradients to have a look at it, because it is a very, very famous attribution technique in deep learning. So I think Wang Chao and Xianglin reported the topics on report papers on similar topics. So the point is that the gradient itself lose some very nice properties. And if we would like to have attribution means that we track the result back to the input. If we want to do this, we need to preserve, just like our visualization, we still need to preserve a set of attribute property there. And this integrated gradient can preserve the majority of the properties, and also can provide a better attribution effect. Okay.
Yeah, and the second class is called surrogated approaches. So what it did is it locally approximates one function f along xi with a simpler function that is then interpreted. So they have two surrogate approaches. One is lime and the other one is sharp. But I also didn't check the details because there are so many of them. And the third,
So here, so it's more like a input transformation technique, right? So called surrogated.
input transformation.
Yeah. So here, if we for the gradients and its variance, it's just apply the attribution methods directly on the samples. But for the surrogate approach, it's trying to transform exit sample with approximation function g. So I didn't get it. So what does f means?
F is the original model. And xi here, I think xi means every pixel. So for every pixel, they locally approximate the original model with a simpler function.
Oh, your point is that we are not approximate x, we are approximate f.
Oh yeah, yeah.
And what's the point we approximate f?
So if you approximate f with the simpler function g, and g is more interpretable than f.
Oh, got it. So more like we replace the deep neural network model
with a simpler function.
like
So
decision tree,
locally,
and then
yeah.
is explainable. Okay.
And the third one is called modified back propagation. So basically, is for every input pixel, they use different kinds of back propagation technique, and output a relevance score.
What's the difference between the gradients? Gradients also use backpropagation.
I don't know.
Yeah, you're
Yeah.
supposed to make it clear.
Yeah, but there's so.
But that is a category. I know there are the 15 methods. And I think it's okay to not tell the difference between expected gradients. Yeah, and maybe you can complement the difference between. I think the gradients and the surrogate approach are quite clear. But
the
modified verification probably just modify the process of the backpropagation. Okay, please go on. And but there's a question I think that why we would bother to modify the backpropagation. Okay.
So other than that, here comes one question: how to compare the similarity of explanations? The one is qualitatively measure that. That means we use our human eyes to directly look at different explanations and see how similar is that. And the second way is to quantitatively measure. They use two metrics. One is called SSIM, and the other one is Spearman rank correlation. So basically, they are just two approaches to measure the similarity between two images or two images, and their range is between 0 to 1. So if the value of metric is close to 1, that means those two images are basically pretty much the same.
Sorry. So here,
yeah.
will you please be more specific about SSIM and the
I didn't check the exact formula of these two metric, but I think they're originally used to measure the similarity between images.
Well, by the way, this paper is published in NeuIPS for NeuIPS, but this is not a paper on the natural language,
really?
Right? So it means that our paper can still consider NIPS as another venue, right? So if we can have Yufan, is Yufan there? Okay, Yufan is not there. So maybe we can check about. Yeah, we can check about how the. We can check about how it is. If it's possible, we look into the venue of NIPS to see whether we can tie down that.
Yeah. And last is the human studies. So the human studies aim for access the reliability of models using the attribution or explanation methods. How they do it is for each participant, they are given a original image, a prediction of the model, and one attribution map, and they need to rate how much how likely would they recommend to sell that model to external customers. Actually, I find it a bit weird if they wanted to compare how or compare what's the most effective explanations for finding bugs, then they need to ask the participants to, like, for example, choose one between 2 or between 3. But instead, each time they are given an image and one prediction and one attribution map, and they are trying to evaluate how likely they would recommend to sell that model, and based on the attribution map. So I think.
What do you mean by sell the model?
Sell the model means, like if in some company and they have a model and they find some participants to evaluate how much they would trust this model, and like
You mean to believe in this model?
Yeah. So sell the model. Yeah, believe in the model. Yeah.
Okay.
But anyway. So the first experiment is aimed on superior bugs. So how they implement the bug is first, they have a data set contains of dogs and birds, and they put the dogs with a background of bamboo forest, and they put the birds in the background of a sky, and train a BVD CNN. They call it BVD CNN to do binary classification. And after that, the network have 97% of accuracy in testing data set on a sky with bamboo test. So that means this neural network is indeed have these superior bugs.
Sorry, maybe I a little bit off my mind.
So you would like to classify dogs and birds, and when the training set is only trained with sky, the background of sky, or and
they have that means because the superior bugs means
yeah, I understand.
yeah.
what is superior bug it is. And about so here that means we train the dogs and birds with background of all the sky, all examples with always background of sky, and then we
dogs only on bamboo forest and birds only on sky.
Okay, I see.
Yeah. So and after that, this neural network have 97% of accuracy on sky with bamboo test. So that means this neural network have this bug. So the assumption here is if you have a superior image and one image with background sky only, then how to say this? If their gradient is pretty much, if the attribution map is pretty much the same.
It's just going to check whether the attribution lies in the animal or in
the
lies
background.
in the background.
Yeah.
So it seems that a lot of attributions. Okay, so I think the majority of the attributions look in both background and the animal, right? And somehow just from the images, it seems that background more or less will be considered as a part of the attribution, right? So still a lot of
Yeah. First, if you look at the result, the attribution map for the background only image and the original superior image is very similar. And when they do quantitatively comparing results, the statistic shows that they are similar indeed. So the SSIM, if it's close to 1, then that means those two images similar. And the SSIM, the SEM means square mean error, I think. Square.
So here, what's the point? So you're given the data, so we somehow need to understand the point. So any takeaway from these data?
What do you mean by?
So what can we take? If there's any takeaway or there's any conclusion we can draw from?
Yeah. So that means, sorry. Basically, all the attribution method can detect this bug because you can see that they did focus on the background.
Okay.
So yeah, that's the only in. And the second, and then the human study. So here they actually have 4 or 5 models. One is normal models, and the second one is called out of distribution, and the third one is random labels, and the fourth one is superiors, and the last one is called top layer. And here we only need to focus on the superiors, the fourth one, and how the participants rate, how the participant think of this model is the red bar, unexpected explanations. That means almost all participants feel that the explanations for the neural network to give that prediction is wrong. But on the left is how likely would they to recommend the model to sell to the customers. And in the fourth column, you can see that actually most of them rate a high score. So that
by
means,
the way, what does the red mean in the right picture? What does the red bar mean?
Unexpected explanation.
Unexpected explanations. Maybe it's a problem of communications. Does the participants really?
But from my point of view, I feel that human study is really weird. But anyway, even though the participant rate unexpected explanations, and still they give a high score for recommend to sell that model. That means because their conclusion is that because the model gives a right prediction, so even though the explanation is unexpected, they still would recommend to sell that model.
Okay.
So yeah, the conclusion is that the participants rely more on the correctness of prediction rather than the correctness of explanation. And then for the mislabeled bugs, how do they implement the bugs is they train 2 neural networks. The first one with a 10% of labels flipped, and the second one is with corrected labels. So the assumption here is if the attribution maps of one sample of a specific sample from the correct model and the wrong model are different, then the attribution method can detect this kind of bug.
No, sorry, let me rephrase it. So if the attribution maps the sample.
So if we have one sample and we have 2 models, right? So then we would have 2 attribution maps. And if they are different, then this attribution have the ability to detect this bug. And if they are the same, then the explanation method are useless.
But
yeah.
But the point is that so somehow one model was fed with a noisy or poisoned samples, but one not. And
because
so
their labels are different, so they are supposed to have different attribution maps. But if they are the same, if the attribution maps are the same, then explanations do not work here.
But if it is but if this label has been flipped, so this flipped label is for training or testing?
Training.
For training. So that means
because
here the correct model and wrong labels, and the wrong label is trained with flipped labels.
Because this is a binary classification problem. So flip means you have a different label.
But how can this assumption to be correct? And suppose if I give in another correct models,
and it is still possible. Suppose I train it in a very different way. It is still with different another kind of reinitializations. It may optimize the parameters in a very different way. So, I still didn't get it. Can you still provide examples and why attribution maps can detect? So detect means
no, the outcome is because the attribution maps for the correct label and the incorrect labels looks visually similar, so they think these bugs cannot be detected by the explanation methods.
no. Let me recap it. Maybe I'm slow today, but I still would like to clarify this point. So we have a model correct, and we have a model which is buggy, right? A buggy model is trained with noise, and giving the same sample S, and they will infer an attribution, right? So even if they are, I think the A, let's say this is A1 and A2, and and does A1 and A2 have to be the same? Not necessary, right?
But the outcome is the same, not the same, but very similar.
May I ask, when we compute the attribute, like for the gradient method, we need to take the gradient with respect to an output label, right?
Yeah, so you would use different label.
Oh.
Yeah, so. Yeah.
But here there's assumptions that there's assumption mentioned that, it means it is.
Because the input for the attribution method are one original image, one prediction. So the label.
So the gradient is taken with respect to prediction, not the ground truth label.
Yeah. Let me think.
I think it is very hard, even if the attribution looks different, it's very hard to infer. I cannot see the causality. I cannot link the attribution map, the difference of the attribution map back to that there is supposed to be a mislabel, there noisy label for that. I cannot have such a link. I think it's very hard to have such an argument. Qualitative, the visually similar.
That just means
what if, let me say, what if I train two models? One model, the crust model, is trained with the appropriate learning rate, and the round model is training in a different or an inappropriate learning rate. So they will have very different accuracy. So they were different. So then they will still have the attribution matrix. When we apply the attribution, when we generate attribution map, and the A1 and A2 is supposed to be different. And in this case, can we infer? But it's not necessarily means that the data has been noise. It is because that I just use an inappropriate hyperparameters. And maybe it's in the case if I use a correct learning rate, I do not initialize the model properly. So which cause the model stuck as a local optima. That is still possible. So suppose I'm using some very weird, maybe Gaussian randomization to initialize the weights, and the second model I'm using her initialization or Xavier initialization to do this. And they may achieve very different results. And how can I draw a conclusion that the reason is just because it is from a noisy data set?
Because here, when I train the two models, the only difference is for the first one, it has 10% of labels flipped. And
yeah, I understand. So maybe the mislabeled data can lead to the fact that the attribution map looks different. But what we want is the reverse. when we see the attribution method is different, and how can we infer what happened, right? There's a huge number of reasons to cause a different attribution map. And how can this help? I don't get that. Maybe they say at least the attribution, or it just means that the attribution map is sensitive to noise flipping.
But actually the result here is in both situations the attribution maps looks similar, and from the quantitative point of view,
Qualitative point of view.
qualitative and quantitative both are similar. So the SSIM, the value of SSIM range from 0.73 to 0.99.
Okay.
So that is a very high value. So that's showing all methods cannot detect this bug. And for a human study, yeah, it's useless. They said participants reject the model because because of the misclassification instead of using attribution method. And the third one is model reinitialize bugs. So they reinitialize the weight of the model, a model starting at the top layer, successively all the way to the first layer. And the model is VGG16 on an ImageNet. So also the assumption here is if the attribution maps are different, when you reinitialize the weight, then this attribution method can not detect this bug, but see there is a problem, and maybe later some expert needs to check that. So what they do is they initialize the weight all the way from the last layer to the first layer. So on the left is a trend model, and all the way to the right is a completely reinitialized model. And they evaluate the attribution maps to the one that is not being reinitialized and see the similarity between them.
What's the conclusion?
And the conclusion is some of them, if the attribution map of a model that is reinitialized and still be very similar to the model that is not being reinitialized, then this model and then this explanation method do not work here. So some of them you can see that. Let me comment. Like those parts, when they initialize some layer, reinitialize some layer, and the attribution maps still quite similar to the original one, then those explanation methods do not work. However, for those, then they will work.
Let's pass the slides. So we need to think higher. So we do not present for the presentation. We present for our publication. Let's keep going. I have something to comment.
Okay.
After you finish.
Oh. Oh, I feel why the mouse might disappear sometimes for Mac. I
don't know.
Yeah. I also have this problem.
Right. But
that's a bug of Zoom.
Not Zoom, but they send. Oh, okay. Yeah. So to quantitatively measure the similarity, they compare different. Oh. They compare. Oh no, sorry. So for the test time contamination, it's out of distribution bug. And how they implement the bug is they find 4 models. The first is a model trained on fashion minced, and the second one is minced model. The third one is BVD-CNN, so the model for birds and dogs we talked about before. And the last one is VGG16 ImageNet. And then they input a image from fashion bins dataset. So the first row actually trained on this dataset, but for the rest 3, this image is one out of distribution bug. And the result is even if this image is out of distribution, but the explanation still look very similar, and the statistic shows that indeed they are very similar. So
keep it going on. So just one of the conclusions that the attribution the attribution method is not sensitive to a lot of the bugs. So okay, so I think you do not need to do. There's no need for your conclusion here. But let's do think about it. Zheng Feng here. Is Zheng Feng? Hello, Zheng Feng. Zheng Feng is not here. Oh, Zheng Feng is here. So here, I think this paper gave us some clue and hints about how we write our own paper. And I think this NIPS paper, I think
when I first read the abstract, I feel interesting, but
yeah, that's okay. Okay, that's okay. So here, I think can you go back to the previous the first slide or the third slide, if I remember correctly. Yeah, this one. This is about characterizations. So Zheng Feng here. So we once discussed about it in our visualization model. Once our visualization model or visualization framework is done, we are going to try how these visualizations can facilitate the bug detections. So in this case, I think we can also try to learn. Hello, Zheng Feng is here, right? Yeah. So in this case, Zheng Feng. So do you remember that we need to train 2 models? The first is the correct model, right? The second is about the incorrect model. So I'm thinking about there's a lot of way to construct an incorrect model. So I think this paper can provide some clues for us on how we construct an incorrect model. So the first is that suppose you're using CIFAR 10 dataset, you can try to flipping maybe 10% or 20% of the labels in China model. And this model is supposed to be a little bit problematic. So we're going to somehow we're going to check how our visualizations can support this kind of bug, and whether the visualization can provide some hints or even allow us to draw a conclusion that when the visualization looks like this, it somehow means that it has a labeling error, so some labeling errors, and also for spurious correlation. Correlations. We can still do the same trick, but we need to prepare another data set.
So you mean we construct a field model by
So we construct 2 incorrect model and 1 correct model. So let me write it. You can just now take the notes. So we have incorrect model 1. So this model is caused by maybe 10% of a flipping label. And we may have another model. This model, I'm thinking about whether we can use spurious correlations. Do you understand what spurious means? It's more like a confounding variable. So for example, if I always, just like Xianglin mentioned, that if I'm looking at the images, I'm going to recognize images of white, classify a cat. But when I see all the training samples are a cat with a cat with a toy inside, a cat with a bed, So sometimes when I detect bad, we may predict that this image contains a cat, but it's not necessarily true. It's just because the data set have such a problem. So in this case, maybe we can still look into spurious. But the challenge here is that what is data set? And how can we construct such a data set? Maybe, hey, Xianglin, does the code of this paper has been published?
Code? I think so. I think.
Maybe we can check that if the data set has been published, Zhengfeng can train the model of the spurious correlation. And in their paper, it's mentioned it's just a binary classification, so that'll be easy.
Yeah.
And the last one, still the correct model, right? Still the correct model. But for this correct model, we may look into the out of distribution data. We look into out of distribution data. So in the correct models, and we collect a few out of distribution data, then CIFAR 10s. So one of the approach is that we apply the data augmentation. For example, we make the image blurred. During blurred, yeah, we use we giving a CIFAR 10 images, we have this blurring version, and then feeding the model to see where it is. Usually the blurring images should be out of distribution samples, should not be distribution STF samples. But of course, you can prepare a few samples. So here, so this is task 1, task 2, and there's task 3. So for this task, giving a correct models, we prepare a few dataset. These dataset are supposed to be the out of distribution samples. We observe how the out of distribution samples is going to work and how our visualization can handle those out of distribution dataset. Hello?
Yeah, I'm still not so sure about the second point. The second
point is that you just search the author's paper or whether they have published.
You just see the result of the visualization.
Yeah, we just see. So we prepare 3 models, and we do not make any contribution for preparing these 3 models or preparing the data set. But we would like to see how our visualizing model can interpret
those bugs.
Those bugs, yeah. And maybe we cannot. Maybe we can see something interesting there. So, but anyway, we need to prepare a few cases for reading paper. So you can think about it. If this paper can be accepted in NeuIPS, and our paper definitely can.
Yeah, but one thing I need to mention is they did a lot of experiments.
Yeah, we can also do a lot of experiments. I think that's more just an
engineering effort.
Yeah, so engineering effort is an effort that as long as I pay my effort, I can achieve something. And sometimes research effort, sometimes, of course, I believe that most research work, as long as you pay enough effort, you can get an outcome as well, but sometimes not. But for engineering, we definitely can achieve that. So the goal is very stable, and just be there as long as we pay the effort and we stretch our hand, and the fruit is just here.
Yeah, and for the last one, the testing, test time contamination. Actually, here we have out of distribution data and mismatch in pre-processing. So I'm thinking we also can do this mismatch in pre-processing.
But mismatching in processing is more like a traditional program, right? Or how do you define mismatch in processing?
That means
how do we define mismatch, and whether there are almost the same problem if I do not match or if I do not process the images, and the images to the model will be kind of out of distribution data. Is that a special form out of distribution?
I think the out of distribution means if your model is trained on means data set, then you put in one image from like CIFAR 10 data set that is out of distribution. And for the mismatch, then
yeah, okay, I agree. So
yeah, and for the mismatch, for example, if you have when you pre-processing your data and you have a mean and standard deviation.
From a philosophical point of view, they are the same. They are the same. So they are
both of them, both cases are the samples, which does not conform to the diffusion of the training data.
Okay. Yeah. Okay.
Yeah. Okay. Hey, Zhengfeng there.
Yes.
If you got it, so you train two models, but the second models you just based on Xianglin's data. If Xianglin can find it, you do the second task. Otherwise, you just leave the V. But for the first task, when you train a model, the first approach is that maybe, so this maybe there's 1.1 and 1.2. For 1.1, you just flipping the data set. So that means when we train the data, we have a lot of noise data, and we train the model. And for 1.2, and this model, maybe you can use an inappropriate hyperparameters. For example, you are using a large learning rate, or you make the model unnecessarily large, or reduce the number of layers in models, whatever you try. So you can, 1.2 means that inappropriate hyperparameter.
Oh.
Hyperparameter.
I see.
Yeah, so you can see. So we have a few models, and so anyway, our flavor is that we would like to provide visualize the framework to infer what's going on, if what's really going on when the model is not right, or what's going on when or in each epoch whether the model has learned, or in which epoch this sample is correct, but in next epoch this sample has been predicted incorrect. So we would like to the model or the framework to answer those questions for us. So in this case, when Xiangling's model is well or is released, and we need to apply these models on these cases to see how this model, that's more like we are answer the so what questions. When the model is trained, it's visualized, and so what? And this questions is unaddressed by deep view. And but anyway, deep view has already been is published book papers in EJKI, and I think we should aim higher.
So this should be combined with the active learning, or should be
separate? No, this is separate. Active learning is a separate work.
Okay, but for active learning, you also say you need to prepare for
still active learning will still prepare. Active learning is another case.
Okay.
Okay, Xianglin and Zhengfeng, I suggest you both.
Oh wait, I let me save this.
Okay.
Screenshot.
Yeah, so that's the part we answering the so what question. So I suggested both you and Zhengfeng record it. So once you're ready here, sometimes you can ask Zhengfeng, interact with him to see how the progress going on.
Okay.
Yeah,
that's all.
Okay, thanks Xianglin and thanks Zhengfeng. Next one is supposed to be Aaron. Hello, Aaron.
Yeah. Okay, on.
Okay, so let me introduce a little bit about this work. This work is a journal paper, and it is going to comparing to the work presented by Xianglin, which is looking into the bug of the AI program. And this work is going to propose the testing approach to see whether there is any bug in a traditional program. For example, if we write a Java, write a Python programs, and we're going to test it. But of course, in the modern languages, there's a lot of, all the modern languages support a concept of the object-oriented programming. So object-oriented programming is somehow proposed by a Turing Award winner. It's called the Barbara Liskov. And then his work not only lay a foundation for object-oriented languages, but also propose a lot of principles. For example, when we are programming, there are some principle called the Liskov programming principles. So that's influence how to design a program. So Aaron just going to show such a Aaron's work here. So the question here. So when there's when the program introduce some user features of object-oriented features. So if we want to test this program or automatically test this program, it needs a lot of new tricks. So Aaron's presentation is going to show a work that allow us to propose a testing approach, automatic testing approach to test the object-oriented programs.
Yep. Yeah. So this paper is called Enabledness-based testing of object protocols. And the authors, firstly is Javier, which is a student in UNGS. And then Gagliotti, which is a assistant prof in UBA.
In Argentina.
And the other two professors are also from UBA. So just an overview of this paper. Firstly, it introduces this concept called the object protocol. It's basically a restriction on the order in which the methods of a particular class or object can be called. So for example, in Java, there's a list iterator class, and for example, you have to call either next or previous method before you can call remove. So this is one of the protocols that this class has. And we'll go through another example later. So they found that 7.2% of all types, it defined some protocols, and 13% of classes were actually clients of types that defined protocols. So this is something that is prevalent in the Java space. So this paper, they hypothesized that it is possible to automatically build an abstraction of the call protocol of an object under test, and then use this abstraction, or exploit this as abstraction to automatically generate more effective test suites. So for object protocols, they can be represented as something called a labeled transition system. And this LTS is basically a tuple. So the first element is a set of labels. So these labels is basically like the method calls of an object. Then the states is just the states of the object, which is just the values of the attributes. Then the initial state is what the object starts at, and the last tuple is the last element of tuple is the transition relation. So it's basically how different method calls change the object state. So basically, it's a transition from one state to another state based on a certain method call.
Based on the definition, so it'll be fine. It is just a very special form of the labeled transition labeled transition system. By the way, the label is actually a typo. But here my question is states. How do you define a state? Because we know that given an object, the object has a structure of tree, right? Or sometimes even graph. For example, I'm reading the examples here. So suppose this is an object called a student, and a student have a teacher of a teacher, right? And teacher have a attribute called maybe friend, and this friend and I will have a attribute link back to the student. So so in terms of the pure or very naive programs, the real world states looks like will have a structure of either tree or graph. And how does the author to define the attributes? Because in terms of attributes, they're all attributes. How can they address those kind of the structure problem?
They never really go into so deep. So like the example they give is quite simple.
Okay, so they didn't mention the problem.
No.
Okay.
Yeah. So this is an example that they used throughout the paper. So it's a bounded stack class. So basically it's just a stack which is limited to maximum of 3 elements. And it has 4 public methods, which is push, pop, and 2 checks, which is whether it is full and whether it is empty. So you can see that when you push an item, they will first check if it's full, and if it's full, then it will throw an exception. And similarly, when you pop, if the stack is already empty, then there's nothing to pop, so it will also throw an exception. So this is like a concrete object protocol, how it really looks like. So we can see at the start, it is C1, which is, we see the 000 is the elements in the stack. So now there's nothing, so they just put 0, and then -1 is the current index. So you can see, for example, when you push an element integer 1, then it will turn to
let's see. So for each state, they were so each transition is more like a method name, right? And a method name in its parameters. And I think it's also simplify the case is that the parameters may not just the primitive value, and the parameters of method can be student object. And how can we present that kind of object is still a little bit problematic. Moreover, getting this state, it has just it have just an array element, right? An array, there's array, each array has a lot of elements, and how do we combine? How do they combine the states? For example, and as far as you can see, a lot of states can be merged, right? It's mergeable. So I suppose they will follow an approach to merge the states.
Yeah.
Okay.
Yeah, that's correct. So you can see, like, actually, if we just do these concrete states, there can be like infinite number of transitions and infinite number of states. So they define something called protocol failures. So firstly, there's a call sequence. So basically, a sequence of calls, method 0 all the way to method n. So I'll show you an example later, but a call sequence is considered valid if it is accepted by the transition system. So for example, for the bounded stack, this is a valid call sequence. So basically you push 1, then you push 2, and then you pop twice. So this is a valid call sequence. But something invalid would probably be like you push 1 and then you pop twice. So the second pop is will throw an exception. So this
it will throw exception. But when it throw exception, isn't the throw exception is another kind of state?
Sorry?
Isn't that exception would be constructed as another state?
Yeah. So as in that's possible. So but the thing is, the call sequence is considered valid if it is accepted by the transition system, which is, for example, something like here. So in this case, you won't see something like push, then pop and pop.
Yeah, what if I start with an S0, suppose with an C0, I call a pop function, then just throw an exception.
There's no exception. As in there will be an exception.
There will be an exception. In this case, it will not appear in this RTA system.
Yeah.
Okay.
Yeah. So all these are just valid transitions. So yeah. So for protocol failures, it is on the call sequences. So there are 2 ways that it can be a protocol failure. First one is if the call sequence is valid, but it still raises an exception when executed on the current object. So that means there's something wrong with the implementation. And The second way it can be a protocol failure is if the call sequence is invalid, but it does not raise an exception when you execute it on the current implementation. So there are two ways that protocol failure can occur. So in both cases, is probably due to a bug made by the developer.
Sorry. So maybe I off the mind a bit. So here you say it is valid according to the intended call protocol. So we define the failure of the protocol that. So what do you mean by valid? And it what it is it means? It means the call sequence.
Yeah, the call sequence.
Okay, the point is that if that call sequence can find a transition sequence in the RTS, but if it still raises an exceptions, it's called a protocol failure. Otherwise, if we cannot find such a label system, we cannot find a label sequence in the RTS saying that if it is not valid, so it will still. The point is that this will not raise an exception.
Yeah, so if it's invalid, you expect it to raise an exception.
But the point is that if it was everything would be fine. It will not throw an exception. But it was not valid according to the build protocol. The protocol means RTS system, right?
Yeah.
So they say it is. So what is the problem here? So the problem means that in the problem of that the protocol has a problem, right?
As in the thing is like,
so here's some question. Yes, here's RTS, but we have to construct. We have to construct a protocol, the RTS, from testing, right? Or where does this RTS come from? Manually provided or we generate automatically?
Yeah. So basically the LTS is the intended transitors. So it should be the truth. So how it's generated is later I'll go through a bit, but usually it's generated by like the preconditions, the preconditions of a method.
Okay.
Yeah. So basically,
it's built through dynamic analysis or static analysis. Dynamic analysis is meant around this method repetitively, and based on its running information, I build the RTS. Static analysis means that I just go through the code and do not run the program.
Yeah, it's static.
It's static. So the protocol is built in a static way. Okay, interesting.
So it means that this is like the intended graph. So we want to see if your code actually follows this graph, which is how we come up with the two failures.
Okay.
So one example of how it can fail. So maybe your when you wrote the code, you made a bug over here. So instead of index minus minus, you put minus minus index instead. So for example, if you have a call sequence push and pop, this should be a valid call sequence. But with this code, when you call pop, you actually produce an index out of bounds exception. So because when you push first, then your index will +1 to 0. And then when you pop, you return minus minus index, which is -1. So this will actually produce an unchecked exception. So this is actually an example of a protocol failure.
Okay. So I'm very curious of how they build the protocol or RTS system. And if you can see, if in line 17, the code has been modified like this, and how could we build a RTS based on the source code? I assume that they build RTS based on the source code, right?
Yeah, so one of the ways is like later I'll go through that. Yeah.
Okay.
So they'll also introduce this thing called enabledness preserving abstractions. So basically is the object protocol, which is a finite LTS. So just now the object protocol, we can see that it's infinite because there are many different possibilities of transitions. So now for EPAs, their states are known as abstract states, which can be seen as sets of concrete states. So from just now the huge graph, you can actually like extract them into these into just three states.
Yeah. So yeah, that is abstract states. And how could we get that?
Yeah. So yeah, I'll show some implementation later.
Okay.
And then so EPA is not something new but this is what they are trying to propose, something called enabledness and exception preserving abstractions, or XEPA. So this is just an extension to EPAs that accounts for abnormal termination of method calls. So they aim to cover all the transitions that are not present in the previous EPA. So the reason they want to do this is they want to confirm the non-existence of any outgoing transitions. So they want to ensure that for any non-existent transitions, if you actually try to execute that transition, there should be exceptions that are true. So on the previous EPA, we just add the pop at the start and the push at the end. So if it's empty and you try to pop, there should be an exception. And if it's full and you try to push, there should be an exception also. Yeah, so this is the extended EPA. So now that you have like two different models, we can talk about the coverage and the fitness functions that they can implement. So for the EPA transition coverage, it's basically just all transitions coverage. You want your test suite to exercise all the transitions in the EPA. So it's quite straightforward. You see just for a test suite, you just calculate the number of covered transitions over the total number of transitions. So just to define it, transition is exercised if at least one of the test cases in the test suite. It calls method M on an object in state A and it evolves to state A prime. And the execution of M must not signal an exception because for EPA, all the transitions are valid.
So this so we are talking. You haven't talked about extended EPA,
Yeah,
right?
just the valid EPA. So these are three different coverage that I will go through. So this is the first one. Then the second kind of coverage is using both the XEPA and or rather using the XEPA. So the XEPA now we have additional the extended transitions. So the extended transitions are in the are basically all the exception transitions. So now we add both of them into our coverage. So similarly, the definition for the exception transition, basically when you call method ME, it should result in an exception of any kind. So this is method ME. And so they do not distinguish the type of exception thrown. So the reason for that is because the number of exception types can actually grow quite significantly. Because it's possible, like if you consider all possible unchecked exception types, then this number can increase by a lot. So, and it would like cause the number of covered exceptions to actually be quite small relative to how many possible exception types there are. So they choose just they choose not to distinguish the type of exceptions thrown. And the third and last coverage. So basically they want to pair up the different transitions. So a pair is defined as a tuple. So Ti is just a normal transition and Tj is a normal or an exception transition. And the third requirement is that the destination state of Ti is required to match the source state of Tj. So for example, this is a valid pair. So basically from state A1 you push, it becomes state A2, and then the second pair is the next outgoing arrow. So from A2 it will pop back to A1. So for the coverage is quite simple also. Basically, just check the ratio of how many of these pairs are covered. So the explanation of why they did this is not very clear, but it's basically because they want to ensure that all possible pairs of method sequences are covered. And from the results data, you can see that actually this coverage is performs the best. And so now that we have some coverage formulas, we can define the fitness function. So for the first one, which is the normal EPA coverage, is
so here there's not supposed to be something like transition distance towards the branch distance, right?
No.
Yeah, I suppose there's no such thing.
Yeah.
Yeah, so I think it's okay. Aaron, you can skip off those coverage stuff. I think the coverage stuff is very abstracted. So I'm curious about how to build such a LTS. So we're supposed to have a ground truth LTS so that the program can execute them, right? And those are all the coverages. And how can we build such a more like ground truth LTS? So that is what's interesting.
Okay. Yeah, so I think that's the last slide for the fitness function. So for EvoC, it allows to natively combine multiple coverage criteria into a single aggregated fitness function. So this is what they did. And they composed three different configurations.
Like the branch coverage and
yeah, correct. So yeah.
Exception coverage, okay.
Yeah. So for the implementation, they also didn't go like very into detail, but these are the examples that they showed. So basically before they can actually build the transition system, they have to create this these methods, which is called the enabledness Boolean queries, and one for each public method in the class. So just now we have 4 methods, which is push.
For transition, each method represents transitions in your TS.
Yep. So these methods, these Boolean queries, basically it returns when the method is enabled. So for example, in order to push something, the stack has to be not full. And similarly, when you pop something, the stack has to be not empty. And for it's empty and it's full, there is no, it's always enabled, so it always returns.
So here, my question is that are those methods automatically generated?
Yeah, so one way is either is manually written by the developer himself, or you can automatically extract them based from the method preconditions.
So it requires the method need to very explicitly mention what is the precondition of that.
Yeah.
And this precondition is written by natural languages or by annotation.
I'm not very sure.
Okay, so it seems that it's more like a semi-automated approach, right?
Yeah.
Because it has to construct the product that requires enormous efforts. Unless this program is very, very important,
yeah,
it was worthwhile for us to write the preconditions and build a protocol. And even if we do this, they cannot make sure whether our protocol, our written protocol doesn't have bug, right?
Yeah.
So you can think about the code itself is just kind of a specification.
Yeah.
And why the code has bug? Because the specification it is not because code is complicated, because the specification conveyed by the code is complicated. So that means as long as we're writing some specification, it's very similar. It is very similar that we're writing some specification. As long as there's it is still introduce some risks. Okay, let's please go on. Yeah.
Yeah, because I mean, I guess in a way it kind of makes sense, because if we try to build an LTS based on the source code itself, then what if your source code is buggy? Then the LTS will also be buggy, and then there's no point trying to find bugs from that, because your LTS is already buggy.
Yeah.
So
sometimes we have to, what I mean is that, if in this case, it's more like we somehow need to build a specification, manually write a specifications, then we test the code against the specification as a reference, so that we're not aware of the bug. So, and also, but the benefits or the advantage is that as long as we can build such approach, when there's an exception or when there's a fault we find, we can even know what is the reasons and how to fix it, and all of them are very clear.
Yeah. So then they just give an example of the XML file.
So that's very label intensive work. If we would like to use it, it will be very label intensive. You need to specify in a very clear way. Okay, please go on.
So for the experiment setup, not much over here, but basically they use like 12 subjects that were previously used in papers studying the EPAs. So the EPAs are
I think let's go through these slides quickly.
Yeah. And for the fault detection, they use mutation analysis. So the first question is how this EPA is compared to other approaches for general failures. So basically any like unchecked exceptions, whether they can catch it. So like I mentioned earlier, the extended one with the pair is the best. So for the mutation scores, you can see that like using the EPA XP or using the combination of Evo plus EPA XP, most of them is ranks the first.
Okay, I think this one, from my point of view, this idea is not good to test the general program because it's very heavy weighted. It's more like it's a heavy gun. Once we, for example, is going to test like SFTP connection, etc. But it will be useful for us to suppose there's a very, very important software. For example, the email server, if we want to test the email server, or if we want to test I don't know. So maybe we can test a protocol-based approach like the network communication. We want to test a very fundamental TLS or HTTP protocol. We somehow it worthwhile to manually build a very large protocol. And this protocol, this year TS, encoding some domain knowledge of this program. It's more like provide a reference. Once we got such a reference, we can test other program. Okay, keep going on. Yeah, I think we can avoid the results. So these results are about p-values and effect size. Yeah. Oh, by the way, so when we are running our experiment, I think we also need to calculate the effect size as well for our own experiment. Okay.
Yeah. So this one they compare with like EvoSuite Smart Mutation, EvoSuite MOSA. So it is statistically better also for most of the subjects.
Okay.
Yeah. And for protocol failures, it's relatively the same also.
Yeah. Okay, let's pause this experiment result. I think we can get it. We have really got a general picture.
Okay. And the last question is whether there's an impact in terms of the structural coverage. So overall, there's no noticeable difference in terms of like the line, branch, and exception coverage. Yeah. So even for those that with lesser coverage, it's just less than 1% difference. So to conclude, this is a test case generation technique that builds and exploits the object protocols to find failures. And they studied different coverage criteria. And they found that the XEPA coverage criteria covering the pairs of transitions, it provides increased failure detection capabilities. Yeah, that's it for
okay, thanks everyone. So it's very clarified presentations. Despite when we talk about this topic, a lot of students are not interested in leave, but that's okay. Anyway, I think it's good for us to know this. Let's talk more about in our individual meetings, and if necessary, we organize a peer programming. We need to make some progress on your FYP soon. So yeah.
Okay.
Okay, thanks everyone. Excellent presentation. And thanks everyone for joining us. Let's call it a day. Bye.
Bye.